All right, so today we're looking at measures of position. Where are you? And I'm going to use you as an example, not just you, but like you as an individual. Where are you? Or if you want to say, or any individual, relative to the population you're in. Okay, let's say that you are 6 foot tall man in this country. You are in the upper 5, 6, 8%, whatever the population of height wise. No, it's not true. You're more like the upper 15% or something. Okay. If you move to Shanghai, China, okay, in that population, all of a sudden, you're in the top, what, 3%? Okay. It just depends on who you're with. And I mentioned this before. I got a buddy who dropped out of high school. Well, I got several friends who dropped out of high school. And one of them, whenever he talks, he's like, "Yeah, my buddy Jay here. Yeah, man, he's so smart. He's got a master's degree. He's even got a bachelor's degree." And I'm like, "Dude, sit the way around." Nuh-uh. I'm like, "Yes, really? Yes." So when I'm around them, okay, you're kind of like, a little smarter feeling, whatever, about some things, about book learning, about stuff that's more like, how come this car doesn't run, Jay? You fixed it. I'm like, yes, okay, but the reason I did is because, and I go off on so the mass airflow, blah, 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 blah. And they're like, but you fixed it. Yes, that's all I care about. Okay, great. I go hang out with friends of mine who are great mechanics and they just start going on and you're just like, okay, I'm kind of stupid here. Okay. It really depends on who you're with. Okay. And again, I think height's one of the easy ones to stand out from a crowd. I was at the doctor's a while back and I'm a little, older, and so I'm obviously old, and I need to lose a few pounds, obviously. And they're like, "Well, no, you look pretty good for being your age." I'm like, "Okay, well, thank you. Sure, I guess." Yeah, a lot of guys my age can let themselves go. All right, and so you're like, "Okay, well, relative to my people around at my age, I don't look great. Relative to how I feel inside, no, I don't look great." Okay. And so we have this idea of who we compare ourselves to. Am I comparing myself to the population of people who are, let's say, early 40s versus mid 50s? Yeah, probably still doing that in my brain. Okay. Um, and so I don't like compare myself with people maybe who I'm the same age with sometimes, right? But then when you're like, yeah, okay, but you have to think about, you are 55. And so when you start looking at, comparing for your diseases, what your shape you're in, blood pressure, etc. Okay, yeah, you look pretty good here. Okay. Now, we are going to be discussing today two of them specifically. Okay, two specific today. So number one, we're going to talk about z-scores, which is a relative. These are both relative position, but this one in particular is one we usually refer to as relative position. Okay, so I'm going to draw this out as if it's this nice normal bell curve. Okay, that is, if you drew a histogram under here, it would be nice and symmetric. Are we with me? Okay, those are the same width bars in case you were wondering. Groom, those little, look, they're the same width. Don't give me any crap. Okay, so from now on, what we'll be doing is I will just sketch a picture like so. That's better. It's not great, but it's better. Okay, here's the average right in the middle. Notice this is the theoretical, or the actual, if you will, or the population average. This is what it is supposed to be, or what it's assumed to be. Okay, how do we know that? How do we assume that to be? Well, historically, the average American male, the average is 5'10". Okay, great. How did you know that historically? Um, well, here, I'll tell you how they do it. So a lot of times you get data from the Army, right? They get a pretty good sized cross section of the American populace going into the Army. Hey, what do? Well, you measure those dudes. Oh, that's handy. Yay. So the military has had records going back eons of time. Okay, that's one spot. You can get reports from doctors' offices, right? So big data, the doctors report things about you, all right? Not necessarily, whether you have this disease or that disease, although they do have to report that. Let's say if you go over there because you've got some STD, the doctors do have to report that or things of that nature, not because specifically to you, but hey, in Columbia County, we're having an outbreak of this disease, or in Columbia County, we have more of this or less of that, or whatever it happens to be. Okay, that is for research purposes. Okay, we don't tie it to you directly, though. Well, when they report it. So they have a pretty good idea of where people are. So this, again, is the average. And then again, we've got our standard deviation. That is, how far is the average person, how far is the person on average from the mean? Okay. And so we talked about this last time. Okay. We said, all right, there it is. Now, what I want to know today is this. If I gave you an actual example like this one here, like so, and I said, hey, the average was here at 10, and I said the standard deviation was 2, well, I could put this off, but there's one standard deviation above the mean. Because of 10, I go over to 12, that's one standard deviation. If I go over to 14, that's 2. And if I go over to 3, that's 16. Okay, if I go the other direction, boop, 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 like so, going the other way, right? That is what this thing would look like. And you're like, oh, that makes sense, I guess. Sure. So listen, this is how much you weighed when you're born. Holy crap, the average kid weighs 10 pounds. That's not true, but let's pretend. If your child comes out weighing 12 pounds, then your child at 12 pounds is 1 standard deviation above the mean. And if your kid comes in at weighing 8 pounds, then your kid is 1 deviation below the mean. Now, Carver, if your child was weighing 5 pounds, you're like, whoa, Broom, I can't do that math in my head. I think you can. I think it's 2.5, Carver. I think it's 2.5. So this one right here, number 5 pounds, is 2.5 pounds, or 2.5, sorry, not 2.5 pounds, 2.5 deviations below the mean. Make sense? Now, why do I say above or below? Because it matters, right? Like, it matters. I might be, Groom, you're 6'3". That's tall. Well, okay, I might be 2.5 deviations above the average in America. That may be true. I'm walking around. If it sounds funny, I'm walking about my house right now. I'm going on a little walkabout. I'm gonna get some coffee. Anyways, you might be shorter than average. Okay, you might be the same distance below average as I am. Okay, above it. And so if I might be 2 standard deviations above the mean, it's possible that you are 2 inches below the mean. Now, we need to make sure we understand that. Are you positive or are you negative? Oh, well, you, because you're below, would be a negative. That's how we're going to keep track of this today, or now on. So when we start doing this, and I say that you are below the mean, then you are going to have a negative score that we're coming up with here in a minute. If I'm above, I'm going to have a positive score. Okay, that's how we're going to keep track of above or below. Okay, and that's kind of a big deal going forward. That's going to hold true as we go through this stuff. Part of what we do in statistics is we standardize things. Okay, we standardize things. That is, we all use the same tools. We all use the same, ideas, same methods, same everything. So it doesn't matter what you're reading about. Someday you're going to go into studying sociology, and some sociology report you're reading about, it says something, and it's going to talk about what I'm talking about today. And in a second, I'm going to actually name what I'm talking about. And you're like, oh, this is about sociology? No. It's used in sociology. It's used in production of anything from tank components, building, war machinery, to nuclear weapons, to working on cancer drugs. The same procedures are used throughout. And it's part of what we call standardizing things. Okay? So if I have this situation here and you're like, wee, And again, let's make this one a fairly easy one to work on. Let's say this time it's a standard deviation of 3. By the way, I will draw this picture about 30 million times this year. One thing that you should notice is, Grim, that's the exact same picture you do on the other page. You just labeled it differently. Yeah, you're right. Well, what do you mean? If you are, in this case, from here over that direction, if you're more than 3 standard deviations above the mean, dude, that's a freakish thing. But it doesn't matter if that's how much the tumor shrank by when you squeezed some goo-kumpucky on this tumor in a petri dish and it just like shrunk to nothing, when all the rest of them were just kind of like, oh, I see a little difference, but this one just dried up like a fish. Just, whoop, done. That's weird. It's just as weird as seeing someone who's 7 foot 5 inches tall. That's, whoa, what? That's just as weird as if the average length of time it takes to drive from Portland to St. Helens during rush hour traffic, the average time is 45 minutes, but one day you did it in 26. You're like, what's up? That's weird, okay? It's very weird. But the thing is, probabilistically speaking, it's just as weird no matter which population it is. And that's why we're doing this, because once we understand how this works, it takes all the guesswork out of it later on. Now, Groom, I understand what it would be if it was 46. It's 2 deviations, okay? Obviously, because I counted, Groom, obviously, but also because 46 minus 40, the difference there is 6, yes? And then if I divide that by 3, because our standard deviation is 3, 6 divided by 3 is 2 standard deviations, yes? And likewise on the other side, 34 minus 40 divided by 3 is negative 6 divided by 3, which is negative 2, okay? That we're doing right there is what is referred to as making a z-score. Okay, so a z-score is simply it's a value. It is how many standard deviations above or below the mean a value is. Okay? Above or below the mean. Okay? Make sense? That's it. So, like, Groom. But what about 35 and a third? I scored 35 and a third on the test. I don't know, dude. Let's ask Betsy. Oh, Betsy. 35.3 minus 40 divided by 3 is... you are negative 1.55 standard deviations below the mean. Okay? Or you're not negative. You're 1.55 standard deviations below the mean is what that's saying to me. Okay? If you look at this from here down, this percentage of the population, I don't know what it is. I have no idea. That's a lie. It's about 8% of the population or something, somewhere in that ballpark. Okay. If I went the other side of this, so 35.33 is what, 4.6666. So if I went 44.66666 minus 40, if I was over here, not 40, yeah, if I was over here somewhere, right? Minus 40 divided by 3. Right? That's because I'm doing the exact same thing, but on the other side. What we're going to see in a few days is oh, shut up, it's the same. So what we're going to see is that percentage-wise from here up, even though my picture kind of sucks, is the same from the other side down. Okay? And that's kind of a big deal going forward. That's going to be a big deal for us. We're going to use it a lot. We're going to use it a ton, actually. Nice. Now, what you're going to see a lot today on the assignment is this. So suppose, for instance, that a fella over here was in a population. Let's say you're taking a test, and the average on this test And the book's probably going to use mu. It's just probably going to use mu, so don't get all weird about it. It's going to be mu equals 73%. Yay. And this person scored a, wait for it. This person scored a 87%. You're like, whoa, that's really good, Mr. Groom. Okay, well, maybe. And the standard deviation for this sample, and maybe your book's probably going to use sigma for this part of it. So I'm just going to go ahead and do that too. Got a 9. Now, another clade, this is Bob. And here is Jody. And Jody got a 75. Jody did better, Mr. Groom. Not so fast, Haas. Not so fast. The average in this class is a 77%. And okay. Who did better relative to their class? I don't know. So the formula, which I don't think I wrote down on the other page, but I'm going to write it down now, is x minus mu over sigma. So it's going to be 87 minus 73 over 9. So clearly, Bob scored above the average, obviously. What just happened? 14 divided by 9 is 1 point. That's weird. Mr. Groom, are they all 1.55? No. Bob scored 1.55 deviations above the mean. How did Jody do? I don't know. Let's find out. Bob did better relative to his group. Relative to his group. Now, does that shock me? What do you mean? Well, not really. I mean, I look at this and I go, that's pretty good. And I can see that in my head. That's pretty good. What's going to come down to is how tightly distributed things are, too. Yes? So Bob did a lot better relative to his group because he's way bigger standard deviation-wise, yes? 1 deviation would have been 82, yes? 2 deviations would have been like a 91. He's a little less than 2 deviations above the mean. Over here, look at Bob. He's 2 percentage points above the mean, but the standard deviation's 5. So he's not even 1 deviation above the mean. Who did better? Bob did better relative to his group. Now, back in the day, I taught next door to this guy. Well, not next door, down the hall from this guy. He wasn't a bad teacher. He retired a long time ago. But he's a big pothead. He's a big old hippie from back in the day. But even though he's a giant pothead and a weirdo, he was actually a pretty decent teacher. But he was really weird about how he did things. And so a lot of the normal kids, like the really smart kids and the really dumb kids, didn't like him because they just couldn't get along with him. But your kids who got B's and high C's, low B kind of kid who I just do what I'm told and I'll get it, whatever. Those kids, for whatever reason, they liked it because it was an easy class, I think. But so he would always come in and go, "Oh, Jay, this is so exciting. Check this out. My kids averaged whatever on this test." And I'm like, "Yeah, that's great, Bob. Your kids got an 80-something, maybe a high 70s, low 80s average on this test. That's great, but that's all you have in your classes, high C, low B kids. That's all you have." And so the standard deviation in his class was tiny. In my class, I would have had like an average of about mid-70s or something. He's like, "Oh, my kids did better than you." Well, first of all, my test is harder than yours, number 1. And number 2, I got kids in my class that are straight up idiots. They'll get like zeros on the test, 5% on the test. I've got kids on the other end of the spectrum, like Mr. Norton, who would have gotten like 110 or something because he did all the extra credit problems and this and that, and it's ridiculous. Okay, plus some, I graded on a curve or something, and you're like, ridiculous. But when you averaged it out, we got almost the same average. In fact, a kid in my class My average might have been 70. Let's just make mine 75. But my standard deviation might very well have been 25. No, maybe not 25. Maybe 15. Okay. In Bob's class, that was literally his name, Bob Craig. He's my neighbor. Good for you. Good for you. Tell him hi for me. In his class, they weren't distributed. They weren't very spread out at all. They weren't very spread out at all because, well, everybody's tightly grouped because everybody came from there. Okay. So if you, let's say Cosette was back in the day, was in this class, Mr. Grimm, I feel like I did pretty good on the test. I got an 85. Oh, good for you. Nice job, kid. Well, okay, so then your z-score would have been 85 minus 80 over 4, which would have been 1.25. Ta-da! Now, let's pick someone on the other end of the spectrum. Not stupid-wise, but not going to get along very good-wise. Let me think. Who in the class is not doing good? I'm really killing time. I know exactly who I'm going to say. I just don't want to hurt their feelings right now. Evie. So Evie scores a. She also scores an 85. Nice work, kid. Awesome. So in this class, 85 minus 75 divided by 15 is 0.666. Who did better relative to the class? Nice job, Cosette. Nice kid. Nice job. You did better relative to the class. Does that mean that you're smarter or dumber or this or that? No. It just means relative to the population, and in this case, taking that test, you did better than Evie over here. This is a way of trying to, quote unquote, standardize things. Now, the problem is, in this case, and we talk about this a ton, when we did this, we were using the same tool. We're learning how tools work, and we're learning how to compare, in this case, Evie to this group of people. And we're learning how to compare Cosette to this group of people. So the tool is the same. What it tells us is the same. But we are not comparing you guys, you personally, because we can't. Because as soon as we take this score here, this 85 in this class, and put it into this class, maybe on this class it holds up better. Maybe in this class over here she gets a 90%. I don't know. Maybe if you put her in this class, all of a sudden she freaks out because she can't get along with Bob, and the next thing I know, she got a 12%. How are you getting? Well, I hate that guy. He's such a jackass. And I'm like, okay, but he goes home and sleeps like a baby because he's stoned. But he goes home and sleeps like a baby every night. He doesn't care about your grades. So what are you doing? I'm like, oh, for God's sakes. So it matters which group of people you're comparing to. But it doesn't say that this person is smarter than that one. Simply, this person scored higher relative to their population. That's all it's all about. Now, and again, it could hold up. It could go either way. Now, suppose in this group you've got Addie and Dominic. Nice, over in this group. And in this group, the average population that you're in scores a 79 on the test. And their standard deviation is 6. And X, your score was 71. And in this group, the average is 83. Quick math in my head. Come on, you can do it. Nope, I lied. Yes. Okay, who did better relative to their group? Now, check this out. Groom, they both got negatives. I know. Whoops-a-daisy. So negative 8/6, which is negative 1 1/3. Yep, I think. And, oops. You can't have two standard deviations, you pig. And so z is equal to 63 minus 83, which is 29ths. Which is negative 2.22222. Who did better relative to their population? Now, a lot of times people will say, this guy did because they got the bigger number. But you see, unfortunately, numbers don't work that way. Okay? Bigger numbers go this way. So who did worse? Who did better relative to their population? This person did. And why did this person? Because they are further to the left. Again, think of it as a test. Let's don't think about it as height or something like that right now. Okay. Actually, maybe height is a good way to think about it. Okay. Who is taller relative to their population? The person who's 2 deviations below the mean, or the person who's 1 deviation below the mean? Well, this person, neither one of them is tall, okay, relative to their population. But this person is less short, if you will, okay? Or if it's IQ, this person is less dumb than this person over here. I said if it was, it's not. We just said this is some test or whatever it happens to be, okay? And you're like, that person did better. So remember, it's always when I said who does better relative to their mean or to their population. Okay, the one who is further to the right on the number line. Does that make sense? Awesome. Okay. That's it. Now, where are we at time-wise? All right. Yeah, I think that's where I want to stop for today, time-wise. We'll pick up percentiles on Monday, and we'll go from there. Have a good weekend.